so this is our honors chemistry lesson video for section 14.3, and this is going to be part 1. So in 14.2, we learned some of the gas laws. We learned Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, Avogadro's law, all different kinds of laws. So now we're going to move on to kind of a combination of all of them, and that's called the ideal gas law. And so what I want you to notice is it has pressure, volume, temperature, and number of moles, which we brought that up in Avogadro's law, but there's no ones and twos. It's just one set of conditions. And then of course we do have a new letter in here, which is R, which we'll talk about in a second. So I'm going to go ahead and write that over here on our new list of formulas. So it's PV equals nRT. So the ideal gas law allows us to calculate volume, pressure, temperature, or number of moles of gas. So it just gives us the most options for what we want to calculate. The other thing is, though, ideal gas law, we need specific units for each variable. So like in Boyle's law, we could have volume in liters, volume in milliliters, it doesn't matter. For Charles' law, we could have, that has volume and temperature. Temperature has to be in Kelvin. But for like Gay-Lussac's law, pressure can be in atmospheres, it can be in kilopascals. Well, for ideal gas law, because of this R that we'll talk about in just a second, we have to have specific units for every variable. So P is of course pressure. You have two options. It can either be in kilopascals or ATM. So if you get torr, millimeters of mercury, anything like that, you have to convert to one of these. I'll tell you why there's two options in just a second. Volume has to be in liters, so milliliters is not an option anymore. N is number of moles. Hopefully the wording tells you it has to be in moles, so if like you're giving grams, you would need to convert to moles. Now here is why all of this happens. R is the ideal gas constant. So you have two that you can pick from. This is why you have two different pressures you can pick from. You can either use 8.31, and if you look, the units for that include kilopascals. So the units are liters times kilopascals over moles times Kelvin. Or you can use the 0.0821. And then if you notice, the units are liters times atmospheres over moles times Kelvin. So that's why I say you have two options for the pressure. So if you have kPa, you'll just use 8.31 as your R value. If you have ATM, you can use the 0.0821 as your R value. And then of course temperature, just like all the other gas laws, has to be in Kelvin. So pressure has to either be in kPa or ATM. Volume has to be in liters. N has to be in moles. And temperature, whoops, I put a T, has to be in Kelvin. Alright, so let's look at how to use this formula. So we'll look at the first one together. So it says a sample of CaCO2, or calcium carbonate, is decomposed, and the carbon dioxide is collected in a 250 milliliter flask. So this would be my volume. After the decomposition is complete, the gas has a pressure of 1.3 atm. So there's my pressure. At a temperature of 31 degrees Celsius. So there is my temperature. How many moles of carbon dioxide gas were generated? So I'm looking for my N value. Alright, so real quick, before I plug into this formula, it's important I have all the right units. So I have 250 milliliters. I need that to be in liters. Well, remember, there's 1,000 milliliters in a liter. So that just becomes 0.25 liters. You're just dividing the number by 1,000. After the decomposition is complete, pressure is 1.3 atm. ATM is okay for pressure. It just means I need to use the 0.0821 as my R value this time. Okay, so pressure is fine. And then of course temperature always has to be in Kelvin. So I'm going to take 31 and add 273, and that gives me 304 Kelvin. So now that I have all my proper units, I can rearrange my formula. So PV equals nRT. I'm solving for N, so to get R and T on the other side, I'm going to divide both sides by RT. So N equals P times V over R times T. So now I'm ready to plug in. So my pressure is 1.3 atm. Again, y'all, if you'll label it in the question, it makes it super easy when you're ready to plug in. My volume, I've changed to 0.25 liters because I needed liters. My R value, remember we have two options, but since my pressure is ATM, I want to pick the R value with the ATM. So it's 0.0821 liters times atmospheres over moles times Kelvin, and then times my temperature, which is 304 Kelvin. So the reason that R has all of these units is just so most of them cancel. So I can see that ATM cancels, that's why I picked this R value instead of the one with kPa. I can see my liters cancel, and I can see that my Kelvin cancels. And so after all that, I'm left with moles, which is exactly what I wanted. I wanted number of moles. So I'll multiply the top, divide by the bottom, and so when I do that, I get 0.013 moles. Now, a common question is to ask for grams instead of moles. They'll say how many grams of CO2. So what you do is you'll still solve for N to get moles, and then you can use molar mass to change it to grams. Okay, so sometimes you'll have to do that. So just be aware that that happens a lot, because a lot of times we want to know how many grams, not necessarily how many moles. All right, so let's look at another one together. If you're feeling confident, you can, of course, go ahead and try the next one. All right, so it says, when the temperature of a rigid hollow sphere containing 685 liters of helium gas, so here's my volume, is held at 621 Kelvin, so there's my temperature, the pressure of the gas is 1.89 times 10 to the 3 kilopascals, so there's my pressure. How many moles of helium, so I'm looking for N, does the sphere contain? All right, so let me check my units. Volume has to be in liters, which it is. Temperature has to be in Kelvin, which for once it is. So don't accidentally change it if I actually give you Kelvin. And then pressure can either be in kilopascals or ATM. It's in kilopascals, which is fine. It just means I need to use the 8.31 as my R value this time. All right, so I have all my numbers, so I'm going to rearrange my formula. So PV equals nRT. I'm solving for N again, so I'm going to divide both sides by RT. So that way, of course, we can get it on the other side. Whatever you're solving for, you always want it to be by itself. So it's PV over RT, so then I just plug in. So my P is 1.89 times 10 to the 3 kilopascals. My V is 685 liters. My R, remember I have two options, but because my pressure is in kPa, I'm going to use the 8.31 this time because it has kPa in its units. So it's 8.31 liters times kilopascals over moles times Kelvin, and then times my temperature, which is 621 Kelvin. So if you look, our kilopascals cancel, liters cancel, Kelvin cancel. I'm left with moles, which is perfect. That's what it asked me for. So I multiply the top, divide by the bottom, and I get 250.9 moles. And so that's it. Sometimes there's more converting than other times. Like in the first example, I had to convert almost everything. In this second example, I didn't have to convert anything. You just got to be careful. All right, so I'm going to erase this because I'm going to put this one up here just so you can see it better. But while I'm erasing, maybe pause the video and try that one on your own. Okay, so I'm going to assume you've paused it and tried it, and now let's look at it together. So remember, I'm going to put my answer up here. So it says tennis balls are usually filled with air or nitrogen gas to a pressure above atmospheric pressure to increase their bounce. If a particular tennis ball has a volume of 144 centimeters cubed, so there's my volume, and contains 0.33 grams of nitrogen. Now this is where it gets a little tricky. They gave me grams. I don't have mass up here, but you can always convert between grams and moles. So if they give me grams, I can change that to moles. So even though this says grams, I'm going to put an N over it, and then maybe just give myself a note. I need to convert grams to moles. What is the pressure, so this time I'm solving for P, inside the ball at 24 degrees Celsius? So here is my T. All right, so on this one, some of you might have gotten stumped right here. Hopefully not, but you might have. All right, so volume has to be be in liters. They gave me centimeters cubed. So I'll convert the volume down here just to save room up here. So we have 144 centimeters cubed. So how do I get between centimeters cubed and liters? Well, if you remember all the way back to chapter 3, gosh, we're only in chapter 14, don't you remember that far back? All the way back in chapter 3, I told you that 1 centimeter cubed equals 1 milliliter. Okay, so because I have centimeters cubed on top, I'm going to follow the golden rule and put centimeters cubed on bottom, and that equals 1 milliliter. So those centimeters cubed cancel. However, I can't plug milliliters in for volume in the ideal gas law. I have to use liters. So I know 1,000 milliliters are in 1 liter. Since I have milliliters on top, I put my 1,000 milliliters on bottom, my 1 liter on top. So now milliliters cancel. So then I just do 144 divided by 1,000 pretty much. That's all we're doing here. All right, so we of course get 0.144 liters, and so this is what I'm going to plug in for volume. All right, next, the issue is they gave me grams and I need to get to moles. All right, so here, I'll just kind of work that out over here. Okay, so we have 0.33 grams of N2. I need to get to moles of N2, so I can use molar mass. So N is 14 on the periodic table, so times 2 is 28 grams per mole. So I follow the golden rule. Since grams is on top, I put the 28 grams on bottom and the 1 mole on top. So my grams cancel. I just do 0.33 divided by 28, and that gives me 0.012 moles. So this is what I'm going to plug in for N. So see, now I have a good N and a good V, and by good I mean correct units. We're looking for pressure. And then last one is temperature. And of course it gave me Celsius. So I add 273, so my temperature becomes 297. Alright, so see again, like I said, sometimes you have more converting like we did down here than other times where we didn't have much up here. Alright, so now that I have a good T value, a good V value, a good N value, I'm ready to solve the problem. So I know that PV equals nRT. So I'm solving for P this time. So to get V on the other side, I just divide both sides by V. So P equals nRT divided by V. And so then I just plug in. So my N is 0.012 moles. Now here's where it gets a little tricky on this one. It asked me for pressure, but it didn't specify if pressure needed to be in ATM or kPa. So depending on which R value I pick, that's going to give me a different unit. So since it didn't specify, like if this was a question that I was grading, I would accept either value. Okay, so the one I personally chose to do was I chose to do atmospheres. Okay, but if you chose to do kilopascals, I have my answer for kilopascals written down too, so I can tell you what that is. All right, so I chose atmospheres, so I chose to use the 0.0821 liters times atmospheres over moles times Kelvin. And then times my temperature, which we decided was, 297. I forgot we're using the problem down there. All that over the volume, which we calculated to be 0.144 liters. So if you look, the moles cancel, the liters cancel, the Kelvin cancels. So see, I'm left with ATM because I chose to use this R value. So when I solved, I got 2.03 ATM. However, if instead you had chosen to use the 8.31 for your R value, then you should have gotten 205.8 kilopascals. Okay, so either of those answers would work, 2.03 ATM or 205.8 kilopascals. Alright, so hopefully so far it's not that bad. The hardest thing about ideal gas law for a lot of students is the converting possibilities. Okay, because some of y'all, it's like no matter what, you just struggle with converting all year long. So the sooner you can stop struggling with that, the easier everything becomes. So there's my answers. Alright, so there are some other applications that we can use where we kind of modify the ideal gas law. So the ideal gas equation can be used to calculate density or molar mass. So density is mass over volume, and molar mass is grams per mole. So if you kind of plug that into our ideal gas equation, you get that density, and here I'll add that to our list. Density is pressure times molar mass over R times T. Okay, so pressure still needs to be kPa or atm. Molar mass clearly needs to be grams per mole. R, again, depending on your pressure, you would pick between these, and temperature still needs to be in Kelvin. All right, so let's look at what it's like to use this formula. So it says, what is the density, so we're looking for density, of carbon tetrachloride vapor at 714 torr, so there's my pressure, and 125 degrees Celsius, so there's my temperature. All right, so if you look, I have a pressure, I always have R, and I have a temperature, but what I'm missing is my molar mass. Well, it told me what the substance is. It's carbon tetrachloride, so CCl4. So I can just add the molar mass up off the periodic table. So carbon's 12, chlorine is about 35 times 4, so when I add that up, I end up getting about 152 grams per mole. So that is my molar mass. Sorry, I'm just trying to draw a little scripty looking in is how they have it in the textbook. All right, so we are ready to plug in, except let me check my units first. So molar mass is supposed to have grams per mole. Pressure cannot be in torr. It has to either be in kilopascals or atm. So let me see what I converted it to on this one just so I can use all the numbers I used. It looks like I converted it to kPa this time. All right, so I took my 714 torr. I know that there are 760 torr in 101.3 kPa. So I followed the golden rule and put the 760 torr on bottom and the 101.3 kPa on top. So torr cancels. And of course you could have converted this to ATM. That's fine too. All right, I'm just using what I did on my paper since I already have everything pre-worked out, so you're not stuck watching me use a calculator. These videos are long enough without me having to use a calculator. All right, so I get 95.2 kPa, so that's going to be my pressure. And then, of course, temperature has to be in Kelvin. So I add 273 to my temperature, and I get 398 Kelvin. All right, so now I'm ready to plug into my formula. So I know density is pressure times molar mass over R times T. And I don't even have to rearrange because I'm already solving for density. So then I just plug in. So my pressure we decided was 95.2 kPa. My molar mass we calculated by adding up CCl4 was 152 grams per mole. My R value, remember I have two to pick from, but since I chose to convert my pressure to kPa, I'm going to pick the 8.31. So it's 8.31 liters times kilopascals over moles times Kelvin, and then multiply by my temperature, which is 398 Kelvin. So if you look, our kilopascals cancel, our Kelvin cancel, our moles cancel, and so I'm left with grams per liter, which is fine. Y'all, density is mass over volume. So like you could have grams per liter, you could have grams per milliliter, you could have kilograms per liter, you could have meters cubed per liter, you could have centigrams per nanoliter. You just have to have some sort of mass over some sort of volume. Now because we're using the ideal gas law, we will always get grams per liter for our density based on the fact that we have to plug in specific units into the ideal gas law. All right, so I just multiply the top and divide the bottom, and so once I did that, I got, oops, sorry, I'm looking at the wrong one. There it is, 4.38 grams per liter. And that's all you have to do. All right, so let me erase this one, and you try the next one. All right, so pause the video, try this one. I'll assume you've done that, and now let's look at it together. So it says the molar mass of the atmosphere at the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. So this time they gave me the molar mass because, of course, the atmosphere of Saturn's largest moon, Titan, is most likely a mixture, so we wouldn't be able to calculate it on our own. The surface temperature is 95 Kelvin, so there's my temperature. And look at that, it's actually in Kelvin. And the pressure is 1.6 atm, so there's my pressure. Assuming ideal behavior, which means we can use the ideal gas law, calculate the density of Titan's atmosphere. So we're looking for density. All right, so grams per mole is perfect for for molar mass, so that unit's fine. Kelvin's fine for temperature, and atm is fine for pressure. I just know I need to use this R value this time, okay, since we have two options for our R value. So let's go ahead and plug in. So our density is our our pressure times our molar mass. I was going to say molar mass times pressure, which is the same thing, but I wanted to use it the exact same way, over R times T. So my pressure is 1.6 atm. My molar mass is 28.6 grams per mole. My R value this time, like I said, because we're using atm for pressure, I'm going to use the 0.0821 liters times atm over moles times Kelvin. And then times my temperature, which is 95 Kelvin. So if you look, my atm cancel, my Kelvin cancels, my moles cancel, and so I'm left with grams over liters, which is perfect for density. So I multiply the top and divide the bottom, and so for that I ended up getting 5.87 grams per liter. Alright, so that is ideal gas law. Like I said, the hardest part for a lot of people is the fact that you have to have specific units, so there tends to be a lot of converting. So if you're struggling with converting, you might need to go all the way back to Chapter 3, Section 3.3 lesson video.